You are looking at an LED shift register. And why is it called a shift register? Well, I will run it and you can see that the data, in this case is just LED lights, is being shifted. In this case, it's shifted to the left. And if I run the thing, you can see the little sign there. It says shift register. And here are the letters of the alphabet. And of course, data is just being shifted from right to left in this case. Well, you're going to build one of these things. Well, it's not going to be this cool, but it is going to be a shift register nonetheless. So you're going to build a shift register that's going to look more like this one. I know it's not quite as exciting as the shift register, which you just looked at, but the concept is the same. You're going to have data coming in, and that data is going to get shifted, in this case, from right to left. And you're just going to use a bunch of JK flip-flops. And actually, let me demo it, and then we'll talk about what's going on. So here I have a 1 coming into the first flip-flop. Actually, let me turn that off. So if I switch this off, now I have a 0 going in. Every time I clock this thing, if I click Q up and C, I'm sorry, up and down for clock, you can see that I have a 0 going in. Watch these lights. See how that 0 got shifted down the line? Now if I flip the data switch back up and I clock up and down again, now I have a 1 moving down the line. If I flip it off, so whatever my input data is, isn't that fun? It's getting shifted. Whatever my data is goes into the first flip-flop, and then it goes to the second flip-flop and third flip-flop every time I clock the thing. And we could just see if you can figure out what's going on here. If I have a 1 coming in, that means I have a 1 going to J, and I have this NOT gate here. So if I have a 1 going to J, I have a NOT 1, also known as a 0 going to K. And you know, if you have a 1 at J and a 0 at K, it will set the output Q to a 1 the next time the clock pulses. In this case is a negative edge triggered clock. So when a clock goes to 0, my output Q will be whatever J is. Again, if J is a 1, it sets Q to a 1, right? That's the set state, 1, 0. Then this flip-flop goes into the next JK flip-flop. The Q goes into the J, the NOT Q goes into the K. So again, you can imagine if Q is a 1, I have a 1 going into J, NOT Q will be the opposite, so that'll be a 0 going into K. Again, that's the set state, 1, 0. So the next time the clock goes, this flip-flop will turn on. Now, if I had a 0 sitting here, like actually, well, I don't have that case, but if I had a 0 sitting here at Q, then NOT Q would be a 1. I would have a 0 going to J and a 1 going to K. That would reset this flip-flop the next time the clock went. So each flip-flop becomes what the previous flip-flop is outputting the next time the clock goes. Let me say that again. If Q is a 1, NOT Q will be a 0. The next flip-flop will output a 1 the next time the clock goes. If Q is a 0, NOT Q is a 1. The next flip-flop will be a 0 the next time the clock goes. The next flip-flop's output becomes whatever the previous flip-flop's output was the next time the clock pulses. And this is what is shifting your data. In this case, it's shifting it right to left. All right, let's take a look at a couple more slides. So the shift register that you just looked at, the one made with the JK flip-flops, is a serial in, serial out, left to right shift register. Remember, data came in and it was shifted down the line to the right, and then it sort of went out the other end. But you can have other types of shift registers. They all involve data getting shifted, quite obviously. But in the first example, when you looked at the sign, data was actually going from right to left. So you can have data going the other way. And sort of the classic example of this is like if you enter numbers in a calculator, every time you enter a digit, well, depending on what kind of calculator, but oftentimes data is shifted to the left, or if you enter like numbers in a microwave oven or something, things get shifted to the left. But you could also have shift registers where data is loaded all at once, and then like it's loaded in parallel, and then it's shifted out. And those are called parallel in, serial out shift registers. And you can also, of course, have shift registers where data is loaded 1 bit at a time, and then the output is read in parallel. So that's what this is supposed to be. Example, data is shifted down the line, and then all at once, maybe a whole byte of data is read at once after it's shifted down the line. And these types of shift registers, of course, are used to convert from serial to parallel, from data entered one at a time to parallel, several bits of data being read at once. So you can convert from parallel to serial or from serial to parallel using one of these two types of shift registers. This diagram just shows that you can also, of course, make shift registers out of D flip-flops. So here's my data in, and of course it's a D flip-flop. So whatever the data is will be the output of Q the next time the clock pulses. And in this case, I just have my first output Q going into the second D, and then so forth. So again, no big deal about this slide. It just shows you can build shift registers out of JK flip-flops. You can also build them out of D flip-flops. And of course, just so you know, there is a chip, a medium scale integrated circuit chip, which will actually work as a shift register. So you don't actually have to even build it out of discrete JK flip-flops. It's all on one chip. So I can load things in parallel in this case, or load things in serial. This particular shift register chip will either work as a serial or parallel input chip, and the same thing with output. The data will either get shifted down the line, or you can read it all at once. So this is a 4-bit, it's called a bidirectional shift register. You can shift it either way you like, but you're not going to end up using this chip. But just so that you know that everything we build out of discrete gates or flip-flops, somebody already designed a chip that puts all of that function into one little circuit there. And finally, this is the very last slide, and I'll make this quick. I am making a sequence detector out of this shift register. So I want this output light Z to light up when it detects a particular sequence. In this case, you can see I have all AND gates here. So I have it going from this last Q. In other words, when I have a 1 here, right, when this Q is on, I have a, this is going to this Q. So when I have a 1 here and a 1 here, and then the next gate, I'm going to the not Q. So not Q will be on when this Q is off. So in other words, when this outputs a 0, and the last one, I'm also going to this Q. So let me do this again. This last light will turn on when I input the sequence 1, 1, 0, 1. So it's detecting the sequence 1, 1, 0, 1. And if I run the thing, and right now I have a 0 going in, so let me flip D on and I'll clock it, and you'll see I'll do 1, 1, and then I'll make D a 0 again. Oops. So 0, oops. And the thing's not on, and now I'll make this a 1, and I'll clock it one more time, and the light should come on. There we go, and the light came on. So this detected the sequence 1101. So you can use a shift register to detect a sequence as a sequence detector. All right, that's it. Get to work on the lab.